Okay, let's take a look at what happens to the end behavior of a polynomial of degree 2, which is called a quadratic function. So we're just going to take a look at a couple of different examples, and then again, after going through this entire investigation, try to generalize the results. So we have a degree 2. So again, pay attention to the degree and pay attention to that lead coefficient and then how it affects the end behavior. We have the degree is 2, the lead coefficient is the number in front of the x squared, which is 3. Let's look at how many zeros we have, how many twists and turns, and then our end behavior. So let's graph this. We could put it in a graphing calculator, but hopefully remember the parabola is going to open up because the a value is positive, and this plus 1 shifts it up 1 unit. So the vertex, instead of being at 0, 0, will now be at 0, 1. And then it's a parabola opening upward, but it's going to have a vertical stretch of factor 3 compared to the parent function. So go over 1 and up 3, so you're going to kind of just estimate where that is. It's about like that, maybe. You get a parabola that looks something like that. So how many x-intercepts, how many real zeros do we have here? And I should have written real zeros for these. Real zeros are the x-intercepts. We can also have complex zeros, and those will not be x-intercepts. And this polynomial, this quadratic, does not have any x-intercepts, so it's still going to have 2 zeros, but they're going to involve the complex unit, the imaginary unit I. And so real zeros, we have none. How many twists and turns, which another way to say that is relative minimums and maximums. And by that, like, we have one little twist right here, so we have 1 twist. Degree 2, 1 twist and turn. When we did our linear function, it was degree 1, and we had 0 twists and turns. Another thing that we're going to try to generalize. And then if you look at the graph, we're looking at the end behavior, what's happening to f of x as x goes to positive infinity. So as we go farther and farther out this direction, what's happening to y? And it's going up, and it's going up forever. So as x gets bigger, the y coordinates get bigger, and they are going to be approaching infinity. And if you look at this, on the other side, as x goes towards negative infinity, so as it gets farther to the left, those y values are still going up to positive infinity. On both sides, the ends of the graph are heading upward to infinity. So f of x, which is our y, is going to what as x goes to positive infinity? Again, the answers are going to be either positive infinity or negative infinity. And for both ends of this graph, as x goes to positive infinity and negative infinity, the y coordinates are going to positive infinity. So you don't need to write the plus sign if it's positive infinity. You can, but you do need to write it if it's negative infinity. Okay, so let's think about how this graph is different from the other one. We have the degree is still 2, right here. The lead coefficient, however, is negative 3. And remember, when we have an a value that's negative 3, what does that do to the direction the graph opens? Hopefully you remember. It's still going to shift up 1 unit, so you're going to have a vertex up here somewhere. But instead of going over 1 and up 3, we're going to go over 1 and we're going down 3. This, that negative flips the graph upside down, maybe a little bit farther than that. If I go over 1 to approximately 3, something like this. So it's going to be a vertical stretch of factor 3. The negative flips it upside down over the x-axis, and the plus 1 moves the graph up 1. So for this function, we have 2 x-intercepts. Therefore, we have 2 real zeros. Twists and turns, we still have just 1 twist and turn. So in this parabola, with the quadratics of degree 2, we had, in the first case, we had 0 real zeros. In the second case, we had 2 real zeros. And if you remember from before, you could also have a parabola that just had 1 real zero if it just touches the x-axis and doesn't pass through the x-axis. So you could have, for a quadratic, you could have 0, 1, or 2 real zeros. And try to think to yourself, could you ever have more than 2? If it's a parabola, you're supposed to answer that yourself. Okay, now looking at the end behavior, as x goes out this direction, the y coordinates are going down towards negative infinity for both sides of the graph. For both ends of the graph, they're both heading towards negative infinity. So f of x, or your y values, go to negative infinity as x goes to positive infinity. They also go to negative infinity as x goes to negative infinity. So notice, when it was degree 2, we had the y values were both going to positive infinity or both going to negative infinity. Our previous video, we looked, degree 1, one side went to positive infinity and the other side went to negative infinity. So just be paying attention to that, and we'll generalize this as we go. All right, cubic functions. Cubic functions are degree 3. So we have a cubic function here for number 3. The degree of that is 3. The lead coefficient, there's nothing in front of the x, therefore it's a 1. Now, to graph this, I got to do a little bit more work, and right now we're just trying to see what happens with when things change, when we have a cubic and that kind of thing. So what I'm going to do is I'm just going to graph it in a calculator. So x cubed minus 6x plus 2. Oops. X cubed minus 6x plus 2. And I'm graphing this in a standard window. There's the graph, so we're going to sketch that. It looks like it is crossing the x-axis over there at about negative 2.5 and about 0.5 and about 2 point something. And we don't need to be really super accurate. We're just going to kind of get the idea here. We're looking at what's happening to the ends of the graph. How many twists and turns can it have? And also, how many zeros could it have? So that's why we're generalizing it and we're not graphing it super accurately. That's not our goal right now. Right now, what we're looking at is those generalizations. So the number of zeros, of real zeros for this graph, we have 1, 2, 3. Degree 3, we have 3 real zeros. The number of twists and turns that you can see, you got, or minimums and maximums, local minimums and maximums, we have 1 right here. We have another one right here, so we have 2. Degree 3, 2 twists and turns. When we had a degree 2, it had 1 twist or turn. Degree 1 had 0 twists and turns. So hopefully you're kind of getting what's going on there. All right, so then the end behavior. As x goes out this way towards positive infinity, the y coordinates are heading up. So as x goes to infinity, f of x goes to infinity as well. On the other side, as x goes out to the left, bigger and bigger negative numbers, these y coordinates are also going down forever to negative infinity. So as x goes to negative infinity, f of x goes to negative infinity. And recall in the last video, you can write this in limit notation if you want to get some bonus points. So this right here, the limit of f of x as x approaches infinity, is how you say this right here. And so it's saying as x goes to infinity, what is the limiting value of f of x? Well, there isn't a limit because it's heading to infinity. So your answer over here is going to be infinity or negative infinity. This is called our end behavior in limit notation. We use limit notation, basically you'll be learning it this year, and then we use it pretty much entirely when you are in pre-calc. Okay, so this guy right here, the limit to write that, the limit of f of x as x approaches, so we're looking at what is x approaching. As x approaches negative infinity, that arrow is saying it's heading towards negative infinity. What's y headed towards? Well, the y values are also headed to negative infinity. So you can write all of these answers in limit notation for some bonus points. Okay, this next cubic function also has degree 3, has a lead coefficient of -1. So notice as when we had a degree 3 lead coefficient of +1, the ends went off to positive infinity as x went to infinity, and negative infinity when x went to negative infinity. So now we're going to graph negative x cubed plus 6x minus 2. All right, gotta remember that. So we have a negative x cubed, I can't remember it, minus, or plus 6x minus 2. Plus 6x minus 2. And these are just random equations that I picked. You can see that it looks like very similar to the other one, but the ends are going the other direction. So we have a graph that looks something like this. Let me look at it again. Okay, let's see if I can get it kind of accurate. Crosses the y-axis down here and goes like this. How many zeros? Well, we have, in this case, we have 3. 3 real zeros. Now, but let's say that if I add a number, a bigger number, so I added -2 here. If I added something, a bigger number, what it's going to do to the graph is it would shift, oops, I'm going to redraw this graph so you can see this. All right, so if I were to shift this graph up by adding a number, I could have, right here I have 2 zeros, one right here and one right here. Oh, I still have 3, sorry. You could have 2 if I move it up a little bit farther, right to there. And then I have just 2 zeros there. I have the one on the right and then this one, where it just touches the graph, the x-intercept, I mean. And you could also, if I shifted it up even farther, this is still going down forever on this side. So you're still going to have this 1 0 right here, but that's it, just 1 0. So you could have up to 3, but no more than 3. You could also have 2, and you can also have 1, but you can't have 0 with a degree 3 because the ends are going off like this, and it's got to cross through the x-axis somewhere. Okay, so number of twists and turns, we have 2. One, oops, get me out of the way. 1 right here, 1 right here. And the end behavior, you try to write it before I do. As x goes to positive infinity, the y values are going to negative infinity. And on the other side, as x goes to negative infinity, y is going up to positive infinity. Okay, we'll save the quintic for the next video and the generalizations.